this is going on. We get to part C, and part C asks about the gravitational potential energy. The gravitational potential energy of the block Earth system to be taken at 0 at the bottom of the loop. So it's basically setting the potential energy to be 0 at this point right here. So potential energy equals 0 at that point. And what would the gravitational potential energy be at the highest point and at point Q and at the top of the loop? So those are all pretty easy questions. Many of you might just reach out and grab the equation and say like, oh well, the gravitational potential energy is simply equal to mg times delta y. You know that, you have that written down somewhere. Well, I hope you also recall that expression for that particular quantity was also something that we found. I mean, we found that explicitly by talking about the change, by associating the work done by a conservative force with minus the change in potential energy. Remember, that was how we arrived at that. So really what we're doing is the exact same thing. We can use the information that we have up here, associate that with the change in potential energy, and use that information simply to basically plug and chug the answers down here when we get to the very bottom. So I think for C it asks from point P to the bottom of the loop, or no, it asks for what the potential energy is at point P, counting the 0 point for potential energy to be at the bottom of the loop. And so in that case, we have the gravitational potential energy, let's put at point P, is going to be equal to mg times 5r, 5.0 r. Part D, what is the gravitational potential energy at point Q? Well, the gravitational potential energy at point Q is going to be equal to mg times r, right? Because that is how much the gravitational potential energy is above this bottom point. And then E is what is it at the top of the loop, right? The gravitational potential energy at the top is simply equal to mg times 2r. Excellent. Then let's see if we can finish the rest of this up. If instead of being released, the block is given some initial speed downward along the trap, do the answers through A through E increase, decrease, or remain the same? Wow, that's a really interesting question. So we give it some initial velocity. What's that mean? Some initial velocity downward means that this has a velocity initially, right? And we know that if we have a velocity, it means we have some kinetic energy. So we have an initial kinetic energy of equal to 1/2 mv squared. Excellent. All right. So as this object starts to move, some of its gravitational potential energy is going to go into kinetic energy. But the actual gravitational potential energy that we calculated here, it really only depends on how high above the 0 point it is. So while this certainly does change the total energy, let's look on a case-by-case basis. In this situation here, this was simply the work done by the gravitational force, and that doesn't change if it's moving. It doesn't matter if it's going near the speed of sound or even. I mean, it's simply a measure of how much work is done by this gravitational force, and the mass and the gravitational acceleration don't depend on how fast it's going. Those are independent of that quantity. Similarly, the displacement also does not matter. Now, how fast it goes through that displacement, that may change, but this doesn't depend on that. There's no time anywhere in this expression. So answers A and B wouldn't change. Those are how much work is done by the gravitational force. And as we talked in previously, that the potential energy for each of these objects kind of depends on this exact quantity. We see that those are not going to change either. Those depend on the mass and the gravity. Even though we're going to get a larger total we're going to get a larger total energy for the system. And it's true that because it started off with some initial velocity at the very top, it's going to have a much higher kinetic energy at the bottom, here at the side, at the very top than it would have under normal circumstances. But that's certainly something that's worth thinking about. Excellent. Let's get to the next video.